Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of optimization problems for calculus. The previous video that I did was kind of a how-to on how to tackle these problems. Now we're going to apply that how-to to all different styles of problems you'll generally see in a calculus course or a differential calculus course. So the first style of problem that I want to talk about is minimizing distance problems. Maximizing distance problems are usually not existing, like that. Who cares about giving the longest distance? We want to minimize distance. So the first one we're seeing here is more of a theory problem than it is an actual applied problem. Find the point on this curve which is closest to the point 5, 0. So how do you tackle this? I've read the problem, so let me go ahead and write out those steps. I've read the problem. To understand the problem, I should probably draw a picture just to help myself really get an idea of what's going on here. So there I have drawn the curve. That's a square root curve. It's shifted to the left slightly. And there's the point that we want to get close to. So I want to find the point on this curve, which could be any of these red points I'm just kind of writing in here. I want to find the point on the curve which minimizes the distance between that red point and 5, 0. So that's how I'm going to understand the problem. I want to minimize this distance. In fact, let's go ahead and just take a random arbitrary point there. We're going to call this point x, y, and we want to minimize this distance d from x, y to 5, 0. So therefore, I've read the problem. I understand what's going on. Step 3, which is label unknowns, is not going to really apply here. And in fact, as I said in the previous video, I'm not going to really use that often. So we're okay with not doing that. Step 4, and by the way, I don't want you to memorize steps either. So I don't memorize steps. I hope that you don't memorize steps either. But just in case that we're working off the steps, I should say this fourth step is just to write a master equation for the variable to be optimized. So the variable that we want optimized is d. We want to minimize that distance. So that's what optimization means. You're either minimizing or maximizing. So let's go ahead and just write that in here. Step 4, we're going to minimize d. And just because I write this a lot, you're going to be writing minimize, maximize a lot. I just put min d, minimize d. All right. Well, what is d? What's a formula, a master equation involving that variable d and the other variables in this problem? Well, you should know from your algebra course how to compute the distance between 2 points. It's the Pythagorean Theorem, really. The distance between 2 points is the square root of the distance between their x values, so that would be x minus 5 being squared, plus the distance between their y values being squared. That is the distance between 2 points. And by the way, you can verify that. If you made a right triangle here, you could easily see that is what's happening, because this y value is actually just y minus the y value for the second point. And this x distance right there is the x value for the second point, 0, minus the, or 5, I'm sorry, minus the x value for the first point, which is just x. You would take y minus 0 squared, add it to 5 minus x squared, and that would equal d squared, or in other words, d is the square root of that. Notice that I didn't care about the order in which I wrote x minus 5 or 5 minus x, because you're squaring it, the order of that does not matter. So that's why I wrote it backwards. All right, So this is our master equation. That is the equation or the variable we want to optimize. So the master equation's right there. The problem is that master equation involves way too many variables. It has d, x, and y. And I really wish that I had a way to relate out one of those variables. And luckily I do. This is our relating equation right there. Wherever I see a y, I'll replace it with the square root of 2x plus 3. That's the whole idea. So our relating equation is stated, so our master equation becomes d is equal to the square root of x minus 5 and quantity squared plus the quantity square root of 2x plus 3 minus 0 and quantity squared. Obviously, that'd just be 2x plus 3. I totally get that. Now, before we then optimize this equation, in other words, before we start hunting for the absolute maximum or absolute minimum of this equation, there are a few things I want to mention. One, this problem is no longer focused on this curve. We have now stepped away from that curve. We only use that curve to set up our problem, but really when I say I want to find the maximum of this equation of d itself, it has something to do with the problem up above, but honestly, it has very little in our brains to do with this geometry in this picture. So let go of that picture once you get your master equation and just reset your brain and say, I want to find the maximum or the minimum of this variable d right here. So that's one thing you need to do. You need to let go of your previous work in a way so that you don't let it cloud your mind. That's very easy to do. A lot of people get to this point and they say, well, but the maximum, this curve keeps increasing forever and ever and ever, so there's no maximum. Well, I don't care about this curve. I don't care about this curve at all. What I care about is that red line D, and I want to make it as small as possible. So often when we do absolute maximum and absolute minimum problems from earlier in your calculus course, we think about the graphs of these things. That up there is not the graph of D at all. So let go of that graph. The second thing I want to convince you of is if you want to minimize D, it's the same thing as minimizing D squared. Let me write that down because it's a critical topic, especially when you're specifically dealing with distances. Minimizing or maximizing a variable d is the same as minimizing or maximizing its square. Think about that. Let's say our distance gets minimized when x is 5. Well, the square of the distance also gets minimized at the very same moment, because if you square all the distances, the smallest value still should occur when d is the smallest. So minimizing or maximizing a variable is the same as minimizing or maximizing its square, as long as the variables are positive, I should say. So, and they will be because these are real world problems. So that's incredibly important because we don't have to actually deal with a square root. We can just square both sides immediately. So this means I'll just grab our master equation and I'll modify the master equation here to become d squared is equal to the quantity x minus 5 being squared plus 2x plus 3. Again, that's just because we're squaring the square root. And now what you want to do is optimize this equation. So let's go ahead and do that. Let's take the derivative implicitly of both sides. So this, remember, okay, maybe I should repeat something here. So when you are dealing with optimization problems, you want to verify that your function is continuous, and this function definitely is continuous. It's a polynomial. So d squared is continuous, and that's all you really need because you're going to use the extreme value theorem for all of these problems. More specifically, I want to say it's continuous from let's see, x equals -3/2 all the way to infinity. That's just something that you don't actually really need to state here, but it is true. D squared is continuous and D is continuous from a -3/2 all the way to infinity. Again, you don't really need to worry about that domain restriction here, but that's just something to note. Which brings up a really interesting topic. When you were dealing with absolute extrema in a previous video, we needed closed intervals. And to be honest with you, you still kind of do need a closed interval here. However, you're going to see something interesting involving the derivative that will help us out immensely. So normally, you would check the edge points and they would be part of your candidates for absolute extrema. And then you would find the critical numbers. So I'm just going to write in here critical numbers. And we'll go ahead and compute those. In fact, let me clean this up. Critical numbers, and then I'll just say we need f prime to equal 0 or f prime does not exist. I know the name of the function's not f prime, but I'm doing that so that I can copy this statement and I'm going to paste it into our work every time that we have to get to this point. All right, let's do this. So I just took the derivative of both sides with respect to x. That's probably the most significant difference between optimization problems and related rates problems. Optimization problems, you're just taking derivatives with respect to the variables that are currently present, versus in related rates, it's almost always a derivative with respect to time. Here, I took the derivative with respect to x because d is a function of x. And this tells us that d prime is equal to, well, everything's divisible by 2, so I hope you don't mind that I'm going to write this as x minus 5 plus 1 over d. Or in other words, x minus 4 over d. Now remember, to find the critical numbers, we want this derivative to be 0 or to not exist. That's what we're looking for. Well, d prime is equal to 0 when its numerator is 0. So we have a critical number at x equals 4. I'm actually going to write that critical number and we'll say x equals 4. And then we also have critical numbers when this derivative is undefined. However, d is actually the result of the Pythagorean theorem, right? It's way up there, but it's the result of the Pythagorean theorem. The only way that d will ever be 0 is if x is, let's see, what do I require? X is, actually, now I'm looking at it, there's no way for that derivative to ever be 0. So, or that function to ever be 0, because it's d is the length between this black curve here and this point 5, 0. That will never be 0. So this is always non-zero. You don't even have to worry about it. And that is often the case with optimization problems. So you do not have any other critical numbers. So now, how do you know if that critical number is a local maximum or a local minimum or an absolute maximum or an absolute minimum? Well, one way you can do it is draw out a number line. Or you could take the second derivative, but I'm not going to do that. Draw out a number line. I'm going to plot the point 4 on there. Remember, the actual domain of our function goes from -3/2 to infinity. I'll just plug in 0 into that derivative. The numerator is going to be negative. The denominator is a square root, so that is always positive. So we know our derivative is negative, which means our function is decreasing. And then after 4, plug in any number after 4 or above 4, greater than 4, like 5, and you will get that the derivative is positive, or in other words, the function is increasing. Thus, this is a local minimum. But remember, that's the only, for the entire domain, that is the only critical number, which basically means your function, your distance function, starts like this and does something like this. It reaches its absolute minimum at 4. So 4 is, x equals 4 that is, gives us the absolute minimum for this curve. So I'm going to go back and read the question. Find the point on the curve which is closest to the point 5, 0. That point occurs at x equals 4, comma, and then the y value is just found from this function, which you would plug that in. 4 times 2 is 8 plus 3 is 11, so square root of 11. 4 comma square root of 11. So some point right about here minimizes the distance. This distance is minimized at 4 comma root 11. So again, just reiterating the steps we went through. We read the problem. If you didn't understand it, you have to draw a picture, which is pretty much always a good thing to do. Step 3, which is label unknowns, we don't really have to do in this case. State what you want to minimize or maximize. We want to minimize D. And in that process, create an equation for that variable you want to minimize. So distance is just the distance between 2 points. And our 2 points are x comma y and 5 comma 0. So we went ahead and set up the distance formula. And then we use calculus to find the absolute minimum. Remember, for a continuous function, the absolute extrema occurs either at the edge points or of a closed interval or at a critical number. Well, in this case, we have two issues, or one major issue. We don't have a closed interval. However, you can kind of ignore that and just say, well, our derivative on the entire domain is negative until we get to 4. So our function, our distance function, is always decreasing until we get to 4. And then our derivative is positive thereafter. So our function is increasing thereafter. So there is no other point on the distance function that is lower than the value at x equals 4, because that would be the absolute minimum. All right. Also, a big piece of information that we use there is in blue. Minimizing or maximizing a variable is the same as minimizing or maximizing its square. That gets used sometimes. Often it doesn't, but with distance problems, it gets used. Let's go ahead and do a second problem. I'm trying to minimize the number of problems that I do in each video here. So this problem is a very classic one. You'll see this in almost any optimization homework. A fence that's 8 foot tall or 8 feet tall runs parallel to a tall building, but at a distance of 4 feet from the building. What is the length of the shortest ladder that'll reach from the ground over the fence and to the building wall? That is a really classic problem. So I've read the problem. Let me go ahead and write that down. I've read it. And now we're going to try to really understand the problem. And this will require us to incorporate some variables. So this is going to be 2 and 3 at the same time. So let's draw a picture. So here's the picture. To the right is the building. There's an 8 foot tall fence, and that fence is 4 feet away from the building. And we're going to grab a ladder, and this ruler will be my ladder just to showcase what's going on. And we want that ladder to reach over the fence and touch the building. But we want the shortest such ladder. And notice, I can shorten up the ladder by getting it closer to the fence, but it obviously, there's a point where the ladder starts to increase in length. So there is a minimal ladder length that we can find. You can see it on the extremes. Obviously, this ladder right here would go right over the fence and touch the building, but that ladder is super long. So if we raise the angle a little bit, the ladder gets shortened. But if we get too close, the ladder will be super long. So there has to be an optimal place to put the ladder. What I'm going to do is just draw in a ladder for now. It won't be the optimal length ladder. It'll just be a ladder. So here is my drawn ladder. All right, I'm going to remove that ruler. So we've read the problem. We should at this point understand I do need to label stuff here. So let's go ahead in this case and label some things. I'm going to label this ladder length L. And I guess that's it, maybe. So trying to build a formula that relates, or maybe I should say a master equation that gives our variable to be optimized as an equation is our next step. So building a master equation. Well, we want to optimize L. So we want to, in fact, I should say we want to minimize L. That's what we want to do. So let's build an equation that involves L. Now you can see that to build an equation that's involving L, it would likely be the Pythagorean theorem. The problem with using the Pythagorean theorem here is we don't know a lot of information, but that shouldn't stop you from trying. You can see that height is h. We have no idea where that ladder is going to hit the wall there. And this distance here I'll call x. At least that'll give us some type of information for building our Pythagorean theorem. And by the Pythagorean theorem, L squared is going to be that quantity x plus 4 and quantity squared plus h squared. Now that master equation right there has way too many variables, right? There's 3 variables there and we only want 2. So we need a way to relate out one of those variables. Well, this 8-foot fence has not come into play yet. So let's go ahead and use that. This is a tactic from Calculus 2. It's also a tactic from pre-algebra, to be honest with you, where you use similar triangles. We know that this side length is h, and this side length is 8. This is 4, and this is x. So I could say h is to x plus 4, so this side is to this side, as 8 is to x. This side is to this side. Those are similar triangles, so you should be able to do that. In fact, I should put right angles in there. And this allows us to relate out the variable h. So similar triangles get used more often as you move through calculus. Specifically in Calc 2, you use them quite a bit. Depends. You don't have to, but you can use them quite a bit. So this tells us that h is equal to 8 times the quantity x plus 4 all over x. So wherever I see an h in that master equation up above, I will replace it with 8 times the quantity x plus 4 over x. And that's what I'll do right now. This implies that L squared is equal to x plus 4 quantity squared plus h squared, but h again is 8 times x plus 4 all over x. And now we have a master equation that involves only 2 variables. We're ready to go. We need to optimize now, which means we need to find the critical numbers of f prime, or of f, sorry. In our function f, in this case is actually L. I just use f here just because, well, that's what most people think in terms of. One thing you should note is that you can clean up, do some algebra before you actually start into this. This might clean up nicely. You never know. So I'm going to do a little bit of algebra, not a lot, just a little, just to see if something nice occurs. So let's see. This implies L squared is equal to, if I were to square everything in this container here, I would get an x plus 4 squared. So you could see that both terms here would have an x plus 4 quantity squared. That might be helpful. 1 plus 64 over x squared. That is kind of nice. If you're wondering what my algebra, how I did my algebra there, all I did was square each of those 3 items. So 8 squared became 64, and that denominator became an x squared. And the numerator with the x plus 4 became an x plus 4 squared. But if you can visualize it, this means that we would have had this. And both those terms have an x plus 4 squared, and I just factored it out. Is this better than what we originally had for taking derivatives? No, actually, I think it's a little bit worse, to be honest with you. So with these optimization problems, you might want to write everything as a single quotient. Not everybody's favorite rule, but the quotient rule can be powerful in these problems. So I'm going to go ahead and do that. As I mentioned, you don't have to do that, but it is something that's nice to do. Now we're going to find the critical numbers of this. So let's go ahead and take the derivative of both sides. We have 2L times L prime is equal to. Let's see, now on the right hand side we have a quotient rule, so that's going to be the derivative of the numerator, which is a product rule, sorry, but that's what it is. 2x plus 4, let's see, to the first times the derivative of x plus 4, which is 1, times the quantity x squared plus 64, and then plus, let's see, x plus 4 and quantity squared times the derivative of x squared plus 64. And that derivative of that numerator is multiplying the denominator. Yes, it's a bit of a mess. Minus that numerator, x squared, oops, x plus 4 squared, sorry about that, times x squared plus 64. And that numerator will be multiplying the derivative of the denominator, which is just 2x, all over that denominator squared, x to the 4th. All right, and we'll go ahead and just checking here really quickly. Yeah, let's just do it. Kind of ugly, but let's go ahead and see what we have in common. I'll leave the left-hand side as 2L prime for the moment. Let's see, in the numerator, you could see that we can factor out at least an x out of both of those and cancel with an x downstairs. So we get an x cubed downstairs. Let's see, what else could we do? Each of those terms, so this has a, I'll use red to showcase it. This term has a 2, that has a 2. So a 2 can be factored out of that group, and a 2 can be factored out of that group. So I'm going to write that 2 out front. You can probably see why. I'm going to cancel it with that 2 in a moment. Let's see what else. I may just do this as a stopover now, which basically means to me that I'm not going to do a ton more factoring, except for in this bracketed group right here, I'll factor out an x plus 4. And I'm left with an x squared plus 64 plus x plus 4 times x. Oops. And we still have a times x on the outside. Nothing wrong with that. And in the second group, I will just leave that as minus, and we'll take our time to that. Minus x plus 4 squared times x squared plus 64. It is a little bit of work, I'm not going to lie. And then, let's see. Now I can divide both sides by 2, and I get L prime is equal to. And I will also factor out an x plus 4 out of that numerator. I'm left with an x squared plus 64 plus x squared plus 4x. That's just from this distributing to each of these two terms. And remember, that group is multiplying by x. So basically what I've done is I have rewritten this group right here, and we're going to go ahead and subtract, and I've factored off a power of x plus 4 out front. So this will just be a single x plus 4 power times x squared plus 64. Not beautiful, but it is what it is, bracket, all over x cubed. I'm sure that this was probably a little messier than I meant it to be, but that's okay. It's not a huge deal. We can still deal with this. Let's see. This will actually clean up. Surprise, surprise. I just paused the video and just double checked that things would clean up nicely, and they do. It takes a while to get there though. So what I'm going to do is distribute this x through and then combine like terms. So if you do that, let's see, we have an x squared plus an x squared, that's 2x squared, times x is a 2x cubed. We have this 4x that's sitting right, I'll use a highlighter actually, because it's a little bit easier. Then we have this 4x right here, but we're multiplying it by x, so it becomes a 4x squared, so plus 4x squared. And finally, we have this 64 multiplied by x is going to give us a plus 64x. And then we're subtracting off this product of this binomial, which is an x cubed, so we're subtracting off an x cubed, and a 4x squared, so we're subtracting off a 4x squared, and a 64x, so we're subtracting off a 64x, and a 256, so we're subtracting off a 256. This looks terrible, but actually cleans up super nice. All over x cubed. Now remember, this is not L prime actually, this is L times L prime. That's important to note because we will fiddle with L prime in a moment. So L times L prime is equal to x plus 4, and now you see the magic that's going to happen. We get 2x cubed minus x cubed is a single x cubed. And then 4x squared minus 4x squared is gone. 64x minus 64x is gone. So we just have a minus 256. That's actually not bad. And this is all over x cubed. Now that x cubed minus 256, that'll be something we can deal with in a moment. Now we need to divide by L. Dividing both sides by L is the same thing as multiplying by the reciprocal of L. The square root of this, is L. So that's kind of important to note. The square root of this junk right here is L. And so off to the left here, I'm just going to make a little note that L is equal to the square root of x plus 4, which x plus 4 squared, which normally you would write as plus or minus. But in this case, it's not going to be a plus or minus. There's a very specific reason for that. It's because of the fact that this is a real world problem. And if you think about x plus 4, the smallest x will be, x is that distance where the ladder is away from the fence there. X cannot be 0 and it will not be negative. So that's x plus 4 is always positive. So you do not have to worry about the plus or minus. Actually, maybe I should say it this way. The length will never be negative. That's another way to just say it. That's probably a better way of saying that. No, I think actually the way I just said it is perfectly fine. Because normally when you take the square root of something squared, it's the absolute value of that something. But the reality is that x plus 4 is always positive, so there's no need for the absolute values. Same thing, x will always be positive, so when you take its square root, again, that'll just be x. The other piece, square root of x squared plus 64, that's going to be positive as well. It's just, unfortunately, we can't really do anything with that, so I'm just going to leave it as a square root of x squared plus 64. So that's what L is. We're going to go ahead and take its reciprocal and multiply both sides by it. So L prime is therefore equal to this x plus 4. Let me write that in there. X plus 4 times x cubed minus 256 all over x cubed, and then times the reciprocal of that L that we have up there, which is going to be x over x plus 4. It's kind of convenient, actually. And also in that denominator is the square root of x squared plus 64. So let me just do this. Times the square root of x squared plus 64. You can see things start canceling. X plus 4 cancels with x plus 4. This x will cancel with a power of that. And our final look at the derivative is an x cubed minus 256 all over x squared times the square root of x squared plus 64. Remember what we want to do, because it's very easy to forget when you go through all these mechanics here. We want to know, when does that derivative not exist, or when does that derivative become 0? Well, that derivative actually always exists for realistic values. Okay, so remember, x is the distance away from the fence. Obviously, you're not going to have a negative distance away from the fence, so x cannot be 0 as well. And the other piece right here, the square root of x squared plus 64, that's never going to be 0 either. So you're not going to have an issue with the derivative not existing. The only other place that you have to worry about is where the derivative becomes 0. And that occurs when x cubed is equal to 256. Now, well, 256 is 2 to the 8th. So let's go ahead and simplify that down. That will imply that x is equal to 2 to the 8/3, right? You took the cube root of both sides. And this will be 2 to the 6/3 times 2 to the 2/3, or in other words, 2 squared, which is 4, times 2 to the 2/3. That's what the optimal value of x is, I guess you could say. So I'm just going to put this as 4 times 2 to the 2/3. Most people would not answer that way because you're going to grab a calculator for this. We do need to ask ourselves, what is that derivative prior to that point, and what is the derivative after? Is it positive and negative, negative, positive? Is the function decreasing, then increasing? What's going on? So plug in to this derivative right here a value between 0 and that 4 times the 2 to the 2/3 power. A very simple value is 1. Your numerator will be negative, your denominator will be positive. So it's negative, so our function is decreasing, or in other words, the ladder length is decreasing until you get to this point right here. After that point, you plug in any number greater than 4 times 2 to the 2/3. Try like 10 or something like that. 10 cubed is 1,000, minus 256 is positive, and the denominator is always positive. So over here, our function is increasing, and so we have found a local minimum, and it's the only minimum for this function because it's the only critical number for the function. And our function was continuous, way up here. There's our function, actually. So our function is continuous. Actually, technically, this is our function, but the reality is that it's continuous for any number greater than 0. So therefore, you have this continuous function. It's decreasing, and it's differentiable. It's decreasing and then gets to a minimum and increasing. So this must be our absolute minimum. That is, the ladder length gets minimized when x is 4 times 2 to the 2/3 power. So ladder length is minimized when x is equal to 4 times 2 to the 2/3. And that's, by the way, in feet. Now let's go back up to the question and see how to answer their question. What is the length of the shortest ladder that will reach the ground over the fence to the building wall? Well, that length is going to be given by this equation right here. And we know what x is, so we're going to take L and plug in 4 times 2 to the 2/3 power. That is going to require a calculator, so I am going to do that off to the side, but this is what you have to do. I mean, this is really what's being asked. What's the shortest ladder that will allow us to get over that wall and touch the building on the other side? And I get roughly 16.6 feet. So 16, let me go back up here, 16.6 feet. Again, that's very rough, but most optimization problems, you're going to have to use a calculator to solve them out. If the question was on an exam and you're not allowed a calculator, it's likely that the question would be worded such that they would say something like, what is the x value that would optimize the ladder length, or that would minimize the ladder length? That way you just get to this point right here. There's no need to go any further. But generally on a homework, they're going to say something like, what is the length of that ladder as well? Okay, that's a pretty robust problem. And by the way, there are other ways to solve this. So I used to solve this without squaring the ladder length and just doing everything with square roots. It still is gnarly. It's still got a lot of algebra involved. And you might be able to do this using angles. But that's not what I'm going to do here because I think that convolutes the issue. So at this point, we have dealt with a couple minimizing distance problems. So in the next video, we're going to deal with maximizing or minimizing areas.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.